Okay, welcome back everyone to these tutorial videos on the theory of computation. I'm recording a few extra videos for you because like I was saying in the announcement, the next tutorial is going to be after the assignment 2 deadline. So I'm going to try to do a few more videos that cover the material that I would have liked to cover in the next tutorial. So in particular, in this video, we're going to be discussing more at a high level and more at like an introductory level, the notions of grammar, production, and simplification, and normal forms. Normal forms. Okay. So these are in the context of context-free grammars. So we're talking about grammar production simplifications for context-free grammars and normal forms of context-free grammars as well. So if I were to define both of these things at a high level, I would say that production simplification is just the process of, I would say, removing or modifying the production rules of a grammar G. So let's call the production rules P of a grammar G, such that the modified production rules P prime are in some, and I'll use this quote, simplified form. So, because what does that really mean? Simplified, like simplified could mean anything. It actually depends on what you care about using the grammar for. So simplified is more like a context dependent term here, where something might be simplified if you care about one thing, like parsing, versus if you care about something else, like representing explicitly some kind of derivation. Okay. So, or in some simplified form. Okay. So these include a few things that we're going to cover like throughout a few of the upcoming videos, but they include stuff like removing epsilon productions. So epsilon productions are literally productions that have on the right-hand side of the production rule only the sort of epsilon symbol or the sort of empty string, right? So i.e. removing things like this, right? The other thing that is also something we'll be looking at is removing unit productions. So removing unit productions are removing productions that look like this, right? So we'll be removing those as well. And the last kind of thing is we'll be removing what I like to call useless productions. So there's a few types of useless productions that we'll be sort of removing. The first one is what I would call sort of non-generating productions or really variables. So a non-generating variable is, if you have something like S gives you A or AS or epsilon, and then A gives you AS or S. No, sorry, gives you AS or, oops, or ASA, right? Then this variable is actually like a generating variable because you can use S, replace it with AS a few times, and then at some point terminate by replacing that final S with the epsilon, and then at the end you get a string of terminals, right? Just a string of terminals. Whereas if you use the variable a, right? So if you jump from s to a and then you start using derivations with a on the left-hand side, um, then you're essentially stuck in the sense of you're never going to be able to get rid of the variable a on the right-hand side, right? Because if you did something like s gives you a, then so now you're at a, right? So now you're using the production rules for a. And what can you do? Well, you can say, well, I'll replace a with as, maybe replace s with epsilon, so I get a. But you can never shake this variable, right? You're never gonna be able to derive a sequence of only terminals. And that's the problem. That's a problem because you care about variables that can actually generate strings. So really this variable is not contributing at all to the strings generated by the grammar. Right? So those are things that we can also remove. Um, and then another classic, and this is a bit even more simple to see. In terms of useless productions, we have unreachable variables. So unreachable variables would be something like if you had these two production rules for, if you had these two variables with those corresponding production rules, you might add some variable like b gives you um, s or a, but if we're assuming that s is the start variable, then you can never from the start variable get to b, right? So this is very akin to like an unreachable state in a DFA. So in an unreachable state, when a DFA has an unreachable state, removing it does not affect at all what the language accepted by the machine is. And so it's similar here, right? If I just say, well, I'm going to take this variable and its corresponding production rules out, it doesn't affect what the strings generated by the grammar are because B was never going to be in any of the sort of generating derivations to begin with, right? So that's another thing that we can remove. So these are the sort of simplification operations that we're going to be looking at. We're going to be looking at how to do each of them in a smaller separate videos. And one important thing that I didn't really mention in the first part of this sort of very informal definition of production simplification is you want to, of course, convert your grammar to a simplified form, but the important caveat, right? So the simplified grammar, let's call it G prime, should generate exactly the same language. Okay. So L of G, the sort of starting grammar, the grammar you started with, must be exactly equal to L of G prime. Okay, and this is just because you want to keep all of the information and all of the capacity of generating that your initial grammar gave you. You want to, of course, convert it to some kind of canonical form, some kind of simplified form, so that you can work with it further. But you don't want to sort of change the essence of the grammar, right? So it's very similar to minimization, where you want to minimize the DFA, but you don't want to create a completely different DFA that accepts a completely different language. Okay, then it wouldn't really be simplification or minimization, right? So that's the important thing to be aware of. So now, production simplifications on their own are kind of boring. You know, you're just like running through a bunch of algorithms to simplify a grammar. And so in sort of in a silo, if you were just doing production simplifications, then that would kind of be brutal. So the reason why we're actually doing production simplifications isn't for the sake of just doing production simplifications. It's really because they allow us to convert grammars to normal forms. So normal forms are what I would call easier to work with, easier to work with forms of grammar, forms of grammars, which are characterized by the type, or really the form, of allowed production rules. Okay. And so, namely, there are two pretty important normal forms that in sort of intro to theoretical CS classes, they're very often presented. The first one is known as Chomsky normal form, named after Noam Chomsky, who's a very famous linguist and also sort of very famous for other things. But in this context, he was sort of developing normal forms in the context of linguistics, because he is a very passionate believer of grammars and of context-free grammars. So that's one type of normal form, which we'll just see in a second. The other one is known as grayback normal form, also named after a researcher in computer science. So Chomsky and normal forms, what they sort of prescribe is they prescribe that every single production rule in the grammar G must have the following form. So if so Chomsky. So we say that G, so the context-free grammar G is in CNF if for every production rule, let's call it R has the form, so a single variable on the left-hand side, of course, because it's a context-free grammar. So context-free just refers to the fact that the left-hand side of the arrow is free of any context, so it only has a single variable. So it's either of the form A, B, C, where these guys are two variables, right? So A is also a variable. Or the other form that a rule R in a grammar that's in CNF could have is A gives you little a, where little a is just a terminal. Okay. Right. So for instance, if you have a grammar like S gives you BC for A, and then A gives you AA or AAB, then this is not in CNF, right? This is not in CNF. It's not in CNF for many reasons, right? So first of all, I have a unit production here. Then I have a string of more than one terminal. That's also bad. And then here I have a mix of terminals and variables. So that's also not good. Okay. And so we're going to see that the reason why we need to go through these all three of these simplification procedures is because once you go through all those simplification procedures, it becomes very, very easy to convert a grammar into Chomsky normal form. Okay. And there are actually a few reasons why we care about Chomsky normal form. First of all, so if you were to ask a very fair question, right, which is, who cares? So the first reason why we care is because assuming a grammar, well, actually, let me write this in this way. So who cares? There's in fact a theorem, right? There's a very important theorem which says that for every context-free grammar G, there exists a context-free grammar G prime in Chomsky normal form, which generates the same exact language. Okay. And this is important. This is important because assuming a language is in CNF is in fact crucial. It's very important. In other words, a synonym of crucial. um, it's crucial for proving the pumping lemma, but not the pumping lemma for regular languages, the pumping lemma for context-free languages, which is used to show that a language is not context-free. Okay? So that's one reason we care. The other reason we care is because in parsing algorithms, so in parsing algorithms, so what is a parsing algorithm? A parsing algorithm would be something like an algorithm where you give the algorithm a grammar G, let's assume it's a context-free grammar, and a string W. And then what the algorithm, the parsing algorithm A is supposed to say is it's supposed to say, yes, G generates W plus here is the parse tree, right? Here's the way to derive W. That's why it's a parsing algorithm. It sort of parses the way to get to W from the production rules, or it says, no, it's impossible, right? No, G does not generate W. So in particular, in the CYKS parsing algorithm, so there's an algorithm which is called the CYK, and I actually like to add S to the name of the algorithm because actually it's a fellow by the name of Ichiro Sakai who actually invented the algorithm, but instead it was named after C, Y, and K, whose names I actually forget. But that's why in credit to him, I like to call this the CYKS algorithm. Anyways, I'm getting a bit sidetracked. The reason why CNF, the Chomsky normal form, is important for the CYKS algorithm is because you have to assume that your parse tree is actually a binary parse tree. Okay. And the fact that it's a binary parse tree allows you to use dynamic programming, and it allows you to use a very sort of very elegant bottom-up approach to trying to find the parse tree or a parse tree for the string W. Okay, so that's the other reason why it's fairly important. Okay, so the CYKS assumes G is in CNF, and so in fact, if you're given a grammar G, then either there's like a subroutine within A that converts G into CNF, or you just assume that G is already in CNF. Okay, and so that's why we care about Chomsky normal form. There's also, I'll just talk about this very briefly, Grayback normal form. So Grayback normal form is a sort of slightly different type of normal form where we say that a context-free grammar is in Grayback to G and F if for every production rule R, um, R has the form is the form. A, so of course, a single variable on the left-hand side, and then a terminal on being the leftmost part after the arrow. And then let's just call this X. So A is just a terminal, and then X is any number of variables. So you can we can abuse notation a bit and say it's from the set V star. If you think of interpreting all the variables as strings and being able to concatenate them together, right? So for instance, if I have the grammar, so this grammar, which I looked at for CNF. So if I look at this grammar, like the same one as here, this is also not in, so this is not in GNF, but it's for different reasons than for why it's not in CNF, right? Because actually these two rules do satisfy the GNF form. So for instance, here I have AA, and then here it's like I have the empty string, right? I don't have any variables. That's fine. That's legal. Then here I have A and then 3 variables. That's also fine, right? But here these two things are not legal because you have to have exactly one terminal here and here, right? So if I had exactly one terminal here and here, then it would be in GNF. So hopefully you're shaking your head because I've made a mistake, right? That's not quite true. So I sort of quickly overlooked the fact. I sort of went a bit too fast and I said, well, AA is respects the GNF rule. It doesn't, right? So this says it has to be exactly one terminal. So this is also not respecting the rule. So you would have to sort of eliminate this A for it to be in GNF. Okay, and there are other sort of applications and uses for GNF, also in sort of parsing and in programming languages, but we won't get to them in the class. But feel free to ask me about them or to look them up on your own time. All right, so this was like a broad overview of normal forms and of simplification productions, really just to motivate the next few videos where I'll actually be running through some algorithms. Okay, so yeah, I hope this was interesting, and I'll see you next time.